Welcome to Kitchen Table Electronics Lesson 5.5, Fourier Analysis of AC Waveforms. We now know how to calculate the response of a reactive circuit to applied sine wave or cosine wave currents or voltages using the complex analysis we learned in the last few lectures. What happens when the waveform is not a simple sine wave or a cosine wave? Well, we could always solve the general problem by writing down the appropriate differential equation for the whole circuit using the differential equations that tell us the response of each reactive component, and then using a computer to solve for the current as a function of voltage, for example. That's something that electrical engineers do frequently, but a useful and simple approach to this problem is to represent some non-sine or cosine wave in terms of its component sine waves and cosine waves. It turns out that this in fact is a very general approach to decomposing functions that are continuous and single valued, and it's called Fourier analysis, and very useful in many areas of physics. So let's consider a discrete Fourier transform. One can write Fourier transforms down as integrals as well as sums, but here is a discrete Fourier transform of some function f of x. So here is f of x, and I've shown it as this nasty squiggly thing. I have made it be periodic in some interval 0 to 2L. So here it is repeating itself every 2L. In this representation here, actually I'm going from minus L to L, so that this cosine can go from minus pi to pi. And here we have the function written out in component pieces. The average, of course, of the sine and cosine terms is 0 because they're symmetrical about 0. So this offset term here has to do with simply the average of the function, and here you see it calculated by an integral over a period. The next terms then are harmonics of some fundamental period, in this case 2L minus L to L, and so when n equals 1, that's the fundamental period that will fit in here. So that's the first cosine, which would look something like this, and the first sine, which would look something like this. And then we have the next cosine, which would be at twice the spatial frequency, and so on. Here are the formulae for calculating these coefficients an and bn. An is just the projection of the function onto the appropriate harmonic for which you are calculating the coefficient, and ditto for bn. So these calculations then can be carried out, if you know f of x, by doing these integrals here. Now I've shown you a Fourier transform of a function of x that is periodic in some distance to L, but of course it could be a function of t that is periodic in some time 0 to 2 capital T, where the frequency here would be 1 over t, and then this variable here would become f. That is indeed how we will represent the expansion of time-dependent waveforms in electronics. So if we carry these integrals out then, where now we have decomposed our function into t, the time, and f, the fundamental frequency associated with the period of the function, we then have terms at the fundamental frequency f, which is just 1 over the period, 3 times the fundamental frequency, 5 times the fundamental frequency, and so on. So, two things to note: we have sine terms and we have odd harmonics. Why do we have sine terms and odd harmonics? Well, in this particular case, the choice was to carry the integral around about with t equals 0 being the origin of the square wave. So at this point the square wave goes from 0 to 1, then halfway through the cycle back to 0, and then at the end of the cycle, the next cycle, it'll be going back to 1. So here's a full period. You can see that it is odd around 0. In other words, this changes sign as you pass through 0, and so projected onto a cosine which is symmetrical about 0, the result of doing those integrals is always 0. Not so for the sine terms. However, for the even harmonics of the sine wave, by the same argument, the integrals also become 0, and one is left with just the odd harmonics. The coefficient turns out to be very simple. It turns out to be just 1 over n for the nth harmonic. So we have 1 for the first harmonic, 1/3 for the third harmonic, 1/5 for the fifth harmonic, and so on. This representation here shows you first of all the fundamental sine wave at the fundamental period of the square wave. Then the subsequent plots here show you the harmonics at 3, 5, and 7 times the frequency, diminished to 1/3, 1/5, and 1/7 of the fundamental amplitude. And then this waveform here shows you what summing these harmonics will give you, and it's already quite a good approximation to a square wave. So we want to measure the Fourier transform of a square wave using our O1 digital oscilloscope. Happily, because it is a digital oscilloscope, even although it's a cheap little oscilloscope, it has built into it an algorithm for calculating the Fourier transform of a given trace of data across the screen instantaneously, pretty much. This is called the Cooley-Tukey algorithm, the fast Fourier transform. And so each trace that the screen made can be displayed in a little box on the right-hand corner of the screen as a plot of the amplitude of harmonics corresponding to that trace. It does it for each trace, so you'll see the Fourier transform flickering as the oscilloscope scans. What is the calibration of the trace? Well, the trace runs from 0 to a maximum measurable frequency called the Nyquist frequency. Now, the sampling rate is the rate at which data is sampled equal to the number of data points across the screen divided into the total time taken for the screen to scan, or 1 over that for the sampling rate. So, for example, if the oscilloscope shows a scan that lasts 100 milliseconds from the left to the right of the screen, and there are 2048 data points in that scan, then the sampling rate is 20.48 kilohertz. Now, the largest frequency that can be determined from such a scan is half of the sampling rate, because you need 2 data points to define a frequency. That is called the Nyquist frequency, and therefore with the time base set so that the total trace across the screen occupies 100 milliseconds, the Nyquist frequency will be 10.24 kilohertz, half of the sampling rate. And so the calibration of your Fourier components plot, amplitude versus frequency, the frequency axis will go from 0 out to 10.2 kilohertz in this particular example. What about the smallest frequency interval you can measure? Well, this is just related to the longest time that you sample. It can't be any faster than 1 over the longest time. So in the case of having a 100 millisecond scan, it would be about 10 Hertz. Now, there is a mysterious thing called a window function that you can choose in the Fourier transform menu. This is actually a very useful thing. What I didn't mention at the beginning of this lecture is that the function f of x does not have to be periodic, strictly speaking. You can simply choose a large enough interval for the fundamental frequency of the Fourier transform such that you don't care about things that happen outside that window, for example in time, or 1 over that window in frequency. The window function applies a correction to the slight distortion of amplitudes that occurs when you take a finite sample of the waveform instead of an infinite sample. But the correction's fairly small, and we will leave the scope on the default window for Fourier transforms, which is called a Hamming window, and it simply multiplies the data on the screen by a function that has smooth tails at short times and longer times. Okay, so now we know what to do. Let's do the lab. This is the simplest lab you have in the whole course. All you need is our friend the O1 oscilloscope with the scope probe for channel 1 attached to the 1 kilohertz output, and let's see what happens. Okay, our trusty O1 oscilloscope is booted up, and we have connected the probe for channel 1 to the test pin with the 1 kilohertz 5 volts peak to peak output, and you see this now displayed. So we are going to call up the fast Fourier transform menu. Before we do that, let's take a look at some numbers. The range of the Fourier transform is going to run from 0 frequency out to the highest frequency sample, the Nyquist frequency. If you take a look at the time base, 5 millivolts per division, and there are 10-20 divisions here, so the total time for this trace then is 100 milliseconds, 5 milliseconds times 20. The sampling rate of this oscilloscope is 2048 samples across the entire screen, and so the sample time at this particular time base is going to be 100 milliseconds divided by 2048. The sampling frequency will be 1 over that, or 2048 divided by 0.1 seconds. So that would be 20480 Hertz. Right, so that will be the sampling frequency. The Nyquist frequency is half of that. And so we're going to see a display that will put frequency from 0 out to the Nyquist frequency based on this particular time-based value. Let's take a look at the math menu. Move it over here because the Fourier transform is going to appear up here. Math, fast Fourier transform, and there it is. Let's take a look at the frequencies that are resolved. You can see some discrete components dying off rather slowly in amplitude. The scale is a log scale. Let's just make it a little more sensitive, 10 decibels per division. And let's measure the frequencies we're looking at using a cursor. So I'm going to move this cursor over here, and then I'm just going to measure with this one. So the first peak is at 1 kilohertz. The second peak is 3 kilohertz. The third peak is 5 kilohertz, 7 kilohertz, 9 kilohertz, 11 kilohertz, 13 kilohertz, and so on. So these are the odd harmonics we expect for the Fourier transform of a square wave. Let's just take a look at how the Nyquist frequency is changed by changing the time spent for a sweep. So let's make it slower. So now you see this is a slower scan, and you see now that these peaks are more widely spaced apart. And let's make it faster. So now you can see the square wave more clearly on the scope because we're scanning a little faster, and you can see these peaks are all squished together. Let's go back to this nice 2.5 kilohertz per division though. That was good for us. And take a look at the amplitude range here. Now it's in decibels. There is a volts RMS scale, but it's not very useful because it doesn't show too many harmonics, and I'm not convinced that it's accurate at all. So let's go back to this scale. What does this scale mean? Well, this is the amplitude of those peaks relative to this marker here in decibels, so it's actually negative going down from here, and the unit of decibels are defined as 20 log to the base 10 of the ratio of this amplitude to the origin here. 20 log 10 because it's conventional in electronics to take power ratios which go like the square of voltages. One other comment here is this thing called the window. This is a special filter that tries to compensate for the fact you do not have an infinitely long train of signal here, but you're taking a finite box over which to sample the signal, and this introduces errors into the amplitude calculation. It's compensated for by putting a filter over this data here, so a window that isn't a rectangle. These are various kinds of windows. Here's the original rectangle, so this is no window at all, and you can see how it changes the sampling. One other comment to make is the distance between frequencies, the smallest resolvable distance. This simply has to do with 1 over the total time for which the scan is taken, and it's slightly modified by this window function here. Alright, let's go back to amplitudes. If we go to this marked cursor and press amplitude, we get now some amplitude cursors. So I'm going to put one cursor here on peak 1, which was the 1 kilohertz peak. Let's go back there and just check that that's right. Yep, 1 kilohertz here. And then I'm going to measure the amplitude of the next peak, jumping around a bit, so this is a little bit difficult to do, but I get that the third harmonic is about 8.8 decibels down on the first harmonic, and the fifth harmonic is something like 12 decibels down on the first, and the seventh harmonic is something like about 15 decibels down on the first, and the seventh is about 17 decibels down on the first. Let's see how we do. You could see those weren't very accurate measurements. So how did we do? Well, here is a plot of the harmonics together with the ratio expected relative to the first harmonic. The measured frequency was perfect. We had a 1 kilohertz square wave, and indeed the first component of the Fourier transform occurred at 1 kilohertz. And then indeed we picked out all the odd harmonics, 3, 5, 7, and 9, much as expected. What about the ratios of the component size for each of these harmonics? So here's the ratio expected from that theoretical Fourier analysis I showed you at the start of this lecture. 1/3 for the third harmonic, 1/5 for the fifth, and so on. What I've done here is to convert these ratios into power-based decibels, 20 log of this ratio. So of course this is 0, that's where our fiducial line went when we made our measurements onto the first component in the Fourier spectrum. Then 1/3 would correspond on that scale to -9.5 decibels, 1/5 to -13.9, then minus 16.9 for a 7th, and then minus 19 for a 9th. These were the values we measured. Of course, 0 is where we put our cursor, so that doesn't mean anything. So minus 8.8, minus 12, minus 15, and minus 17. We are within about 2 decibels of where we expect to be. This corresponds to about a 25% error in amplitude, but I'll tell you what, that's not bad for a cheap little PC oscilloscope. Well, with that, we end the major portion of the labs for this class. Thank you for listening. There's one more lecture to come of, I hope, some general interest, and then we're all done.